hard for me to introduce this next scan speaker for you because it's probably requires a long list of things for me to go through. But the simplest that I will start with, which is I'll introduce the person who hired me 20 years ago. There you go. Professor Marshall Thompson will talk about part of his Smith lecture from 2 years ago, where he presented it in North Carolina, actually Raleigh, North Carolina, during the ISAP conference. I guess this was fourth Smith lecture, maybe third or fourth, or third Smith lecture. It was 2 years ago. Marshall.
Thank you, Errol. We made a good hire, by the way, when we picked up Errol. He had his prof at Georgia Tech was a good friend of mine, Dick Barksdale, and Dick's had high regard for Errol and his work, and we picked him up, and he's been a very successful staff person. So my presentation today is entitled ME Flexible Pavement Design Challenges and Issues. M&E, I had Ernie Berenberg and I one time. Do I need that? Okay, here we go. Is this on now? But Ernie Berenberg and I one time were doing some work with NCHRP 126. We were at a meeting in Carolina, and one of the folks in the audience said, "Hey, what's M&E stand for, Marshall and Ernie?" And I said, "No, it's mechanistic empirical." So moving right along, this has been a situation where over the years there's been a lot of advancement in pavement technology, materials technology, and we've tried to include that in, quote, ME flexible pavement design over the years. We still have a lot of problems. First of all, the actual road test was finished up in the late 50s, and in the analysis of the road test, there was this decision to make as to whether we go with a scheme based on the structural number, which is empirical, or go with a, quote, mechanistic types approach, which would be based on deflection. If you look at the road test, you'll find that in reality, we could predict the performance of the road test pavements as well from deflection-based data as from structural number. And the idea that there was a high degree of correlation between deflection and rutting was established at the road test. So the determination was made, though, to go with structural number as opposed to deflection, although that data has been very helpful. If you look at the relationship between the deflection here and the number of load reps to a PSI value of 2.5, you'll find that there is that relationship where L is the axle load and kips, D the deflection of mills. So that relationship was firmed up at the road test. This shows that particular plot. In a graphical form, notice we got creep speed deflection versus the log of PSI to a PSI of 2.5. So once again, deflection does relate to performance based on the road test data. So another one showing creep speed deflection versus average rut depth, and as you can see, the R squared was 0.6. It's not the best R squared, but at least it does confirm that, hey, there is this relationship. Okay, textbooks. You'll find that beginning in 1959, there was an interest in moving ahead in pavements engineering. L.D. Yoder from Purdue at that time was an associate professor, mind you, and this particular textbook, Principles of Pavement Design, showed up. I was a beginning grad student in the fall of 1960. We were really glad to see that book. Moreland Heron taught the course. And L.D. and Matt Witzak, most of you would develop a familiarity with Matt through your studies, I'm certain. in 1975 updated that analysis book, The Principles of Pavement Design. And then the other one I think probably has gained a lot of traction over the years is Pavement Analysis and Design by Y.H. Wang, University of Kentucky. His first one showed up 93, and he had a revision in 2004. Okay, some of the early activities in mechanistic empirical design, I would suggest that ME design got kicked off at the first Ann Arbor conference. That is now the International Society of Asphalt Pavements in 1962. I attended that meeting, and there was a lot of information at that time coming in from the folks in the United Kingdom about ME design, et cetera. And so quite a few good articles and good papers showed up in the 62 Ann Arbor conference. We have Asphalt Institute kicking in 72. Probably the next major pop in ME design was the Shell Pavement Design Manual, showed up in 1977 in some of the work at Ann Arbor, and then they published their work in 79. That approach is still utilized, still a lot of good information. If you've never been exposed to the Shell Pavement Design Manual, it's a good opportunity to learn something about how things were considered early on. The South African Pavement Design Procedure, these folks have been doing a lot of work from the get-go in ME design. So they were at the 77 Ann Arbor Conference. We get the Asphalt Institute with several of their publications, the MS-11, the 86 AASHTO Guide. Once again, the 86 AASHTO Guide said, let's do structural number stuff. In reality, though, there are sections of that guide where there is ME type approaches that are considered. NSHRP 126 was the first national effort to kind of pull the things together on mechanistic empirical design. Ernie Berenberg and I headed up that project. We had a lot of other participants that worked with us from the concrete industry. I apologize for that, but nevertheless, they're good guys out there. We're in concrete. But we had folks in the concrete industry and also from the Asphalt Institute helped us out on that project. And then you get AASHTO Aware, which came out of NSHRP 137A and AASHTO ME 2007. This is a project that basically initiated the MEPDG, the Mechanistic Empirical Design Guide, that AASHTO now markets as AASHTO ME originally, and then there's now called AASHTO Aware Pavement ME. That is available through AASHTO for a considerable cost. We've got other efforts in the area. For example, we came on board with the mechanistic empirical design for full depth asphalt pavements in 1989, have been using it successfully ever since. Matt Witzak's done a lot of work in ME design. This is one of them, the third International Conference on the Structural Design of Asphalt Pavements. That's the, quote, Ann Arbor Conference, really, in 1972. And the Asphalt Institute is carried along with their work, and they've got MS-11, which is thickness design for asphalt pavements for airports. That's work that Matt did. And then in 77, the Institute started working in ME design, and their first MS-1 came out in 1981, and they continue to update some of their activities. Okay, let's look at ME design from the standpoint of what do we need to provide for inputs and how do we massage those inputs to develop a final design. We've got paving materials characterization, subgrade soil characterization, traffic, climate. We need a structural model to predict pavement responses. Critically important is the idea, how do we translate responses into predicting performance? And then we need to always take into account design reliability. You're going to, you know, if something is designed to last based on average inputs, it fails half the time, right? Okay, so we don't want that to happen too often. So we need to factor that in, get a prediction on our distress development, and from that into performance. How does distress develop as a function of time? Finally, we wind up with a final design. Okay, resilient modulus inputs for ME design. This is not a new issue, folks. Notice the date on this, 1999 TRB. I did a presentation at a workshop in terms of, hey, where are we with resilient modulus testing and evaluation? I think that figures out, what, 17 years ago, maybe, something like that. And we're still working on that problem, but we're getting a lot better at that particular issue. If you look at resilient modulus, we have a repeated deviator stress. We measure total strain and recoverable resilient strain modulus, resilient modulus, repeated deviator divided by the resilient strain. Fine-grained soils are stress softening. The higher the stress state, the lower the modulus. This is a typical one that we developed years ago and used in our work in Illinois for the Illinois DOT, showing the modulus as a function of deviator stress. Interestingly enough, somewhere around 6 psi, you start finding the effective stress state drops off considerably. That's not a magic number, but it's a good number. And so beyond 6 psi, you'll find the modulus does not change a whole lot as a function of repeated stress state. In fact, in the Asphalt Institute, they suggest if you're developing an input for their particular approach, pick a modulus based on a repeated deviator of 6 psi. Okay. You can also then look at the effect of various factors such as moisture content. Here we've got a particular soil IPA that sells for about $14,000 an acre in northwestern Illinois. But at optimum moisture content, a little bit on the dry side, then we're at optimum plus 1.8%, a huge impact. So we have material very sensitive to moisture content. There are other ways of representing the stress dependency. For example, the semi-log model is one that's used. We've got that in ILLIPAVE. If you take that same data we showed in the arithmetic plot, show it on this kind of a plot, you'll find once again that you can capture the effect of the stress state on modulus. The model that's currently employed in the mechanistic empirical design guide is this one, and you'll find that it's got a input for theta, the bulk stress, as well as the octahedral shear stress, and from that you can predict the resilient modulus. This particular model, notice we've got a K2 and a K3, and that kind of complicates things. Once you get beyond 2 parameters, I really get concerned as an old farm boy. You know, I like simplified stuff that still captures the major effect. But you'll find, for example, in the analysis of the LTPP test data from the various sites all over the state, there was not a very consistent effect of K3. In fact, in some cases, it went the wrong way. And so this model is, I would suggest, one that is very sensitive. You need to know from your test data exactly what those values are. Okay, some of the effects that we need to consider. A degree of saturation captures the effect of moisture content on modulus. This is not what you would call a real good relationship. It certainly captures the trend. If they get wetter, particularly on the wet side of optimum moisture content, you're going to lose values on your modulus. Hey, how about a freeze-thaw cycle? We don't live in a world where it doesn't freeze, particularly in areas like the Midwestern part of the United States. This shows modulus for Tama B, which is a soil, once again, northwestern Illinois. Again, that particular soil looks pretty good without any freeze-thaw cycles, but you put some freeze-thaw cycles on it, all of a sudden the modulus drops off by a considerable amount, a factor of 2. Now, there's one thing about this that's even more disconcerting. Notice whether you get 1 freeze-thaw cycle, 5 or 10, you get a considerable reduction. In other words, 1 cycle is enough to trash you out and drop your modulus down to a very low value. And that's not good news for us. How do we get these modulus values? That ERI value is the modulus at a repeated deviator of about 6 psi. We can actually do the testing. We have found that we can develop that from falling weight deflectometer and back calculation procedures. And from that, tying into pedology and soil series, you can say, hey, if you've got this particular soil series, you're probably going to have these kind of moduli values with the various layers. Or we can estimate it based on strength, unconfined strength, CBR, dynamic cone penetrometer. The folks at Purdue years ago developed a real straightforward procedure. They took a static stress strain curve and found they could estimate what was going to be developing in terms of repeated load moduli values for fine-grained soils. I'm surprised that Indiana has not picked up on that, but they haven't. But it's an excellent piece of work. I don't know whether Errol includes that in the transportation soils, the work from Purdue, stress strain, static work. Yeah, okay. And of course, there's always typical values, right? Yeah. So there are a lot of ways of developing those inputs. The thing about subgrade moduli, there's no such thing as a fixed value. It changes. Moisture content, freeze thaw, etc. And all of a sudden you get a different subgrade modulus value that's going to impact what's going on with the pavement response. Subgrade variability, it's huge. You do back calculations for 5 mile of pavement, the coefficient of variation might be 50% on the back calculated value of modulus. You'll find that there's a lot of lab testing variability from the standpoint, the value you get in the field using back calculation in some models, ELP programs, for example, don't match up very well with what you get in the lab. So you've got to kind of bridge that. We don't have that problem with our particular scheme with ILLIPAVE where we account for stress dependency. These are the subgrades that we typically use in ILLIPAVE and Illinois DOT, stiff, medium, soft, very soft. We find in most cases we're talking medium and or weaker grades. Okay, if you're interested in a good summary, Andre Pupala put this together back in 2008, InChirp Synthesis 382, did a real good job pulling together a lot of data and information on how you develop an input value for subgrade modulus. What's the subgrade modulus? It's still an issue for you to ponder about and consider. Granular materials, they are stress hardening. Stress states go up, they get stiffer, and thus they have a peculiar behavior. The 86 guide picked up on some work that Gary Hicks did at California with Carl Montesmith for his thesis on resilient modulus testing of granular material. And this particular model, K theta to the K2, was developed, and it's one I still like and use. I think it captures the major effects. You can add some things in if you'd like, but nevertheless, this does capture the impact of the stress state, which is theta, the bulk stress. Okay, these are some suggested values for theta from the 86 AASHTO guide. They have values for K1, K2, for base and subbase. A ballparky value a lot of people use is 5,000 theta to the 0.5, where all the inputs are in PSI. This is AASHTO base, AASHTO subbase. They're looking at some suggested interim values that might be appropriate. Back many years ago, Gonzalo Rada, who was one of Matt Witzak's students at the time, they pulled together, they did an evaluation of all the data they could find. A lot of my numbers are in there as well from our early work on modulus testing of granular material, and developed a relationship between K and N as shown here, okay? So if you have an idea of where you are and you do a test and you get something plotting down here, you may find that you've got a bug in your testing approach and your data, okay? If you're not following somewhere along that line close by, you're probably not doing it correctly. So we need to keep that in mind. This is for all the data. If you look at various types of materials, you'll find that in general, there is an effect between silty sands, which are down here, and we get crushed stones, et cetera, that are plotting up here. But they all have the same general relation. Log K is A plus B to the N. And thus you're back into this idea of, okay, what's theta? What kind of stress states do we actually develop in a conventional flexible pavement? Well, this showed up in the 86 guide for recommendations for that value. This is the modulus of the subgrade. This is the thickness of the hot mix, and that's the suggested value for the theta value. Okay, so if you get a theta, you know K theta to the N, you can estimate what the modulus would be. Okay. Then if you want to do this for subbases, then you're back to where you've got stress states, theta values that are quite low, 10, 7.5, and 5. Well, this is the generalized model that's in the MEPDG, the Mechanistic Empirical Design Guide, AASHTO-ME as it's now called. And notice we do have our theta value there. And also this tau octahedral is a calculated value from an elastic layered pavement analysis program. So in this case, you still have to do your materials testing or assume some typical values for K1, K2, and K3 in order to make an estimate of the modulus. Okay. Harold von Quintus pulled together a comprehensive analysis of the data developed in the LTPP lab testing program. It's a good piece of work. Shown here, 1993 AASHTO guide. Now this was in support of a 93 guide because in that particular guide, they developed a correlation between the coefficient for granular materials, base, subbase, and modulus. Okay, what's the modulus? Well, this was what this report was directed toward, was how do we get a modulus for estimating a coefficient to do thickness design. So there was a taste of, quote, improvement from the standpoint of mechanistic empirical in the 86 and the 93 guide. This shows up in Harold's work, but it's actually based on FAA work by Walter Barker and Neil Brabston down at Waterways Experiment Station. And this suggests that the modulus of a layer is a function of the modulus of the layer beneath it, okay? So modulus of layer n plus 1, that's the lower layer, and then you move on up the line. If you know this modulus, you can estimate the modulus of the subbase and the base course for various thicknesses, okay? This is incorrect, folks. This doesn't work. This is not what controls the modulus, the granular material of conventional flexible pavement, hot mix asphalt over granular base. The AASHTO, or the Shell Pavement Design Manual, they've developed some approaches for estimating modulus. And once again, they're tying it into the modulus of the underlying layer and the subgrade. So this is their approach. Once again, I think that it's leading us the wrong way. What really controls the modulus of the granular material in conventional flexible pavement is the modulus and the thickness of the hot mix asphalt layer. What controls the stress state in a granular base? The thickness and the modulus of the hot mix asphalt layer. Now this is work that I submitted in a discussion at the 5th International Conference at Delft. We looked at various asphalt thicknesses, modulus of the hot mix. This is a particular, that value, that modulus of 9,000 theta to the 0.33, that's a reasonable representation of the AASHTO road test base course. Some work we did, repeated load testing on that. If you plot this up and look at the granular base modulus as a function of ET cubed, what's the stiffness of a beam? ET cubed, something like that? Pretty close? Okay. If you look at log ET cubed over 100, where E is in KSI and T is in inch, and plot that against the granular base modulus based on that previous data, this is what you get. So, you know, we need to factor in the fact that if we have thick surfaces and high modulus surfaces, the modulus developed in granular materials will be quite low. We ran some millipave analyses to demonstrate this effect, kept the modulus of consistent at 500 KSI, 4, 6, and 8 inches. The hot mix, a 10-inch granular base. Notice it's 5,000 theta to 0.5. That's a ballparky, reasonable input for a crushed stone. The friction angle, 45 degrees. We looked at subgrade soils, soft, medium, and stiff. That's the ERI. That's the breakpoint modulus, 6 PSI. And you can see we got 3, 7, 7, 12, 3. This is a more fairly typical value. That's the unconfined compressive strength. Divide QU by 4.5 and you get a ballpark estimate of what? CBR. So you can see here, if you look at the modulus of the granular base as a function of the thickness of the surface course, you'll find that the base modulus varies, obviously, to some degree. But this is the midpoint value of the modulus. That's the average for the 10-inch layer. Now, for those values, you'll find that that theta value is this value here divided, appropriately corrected to 5,000 theta to the 0.5. So you can see these theta values are varying from what, 20 psi down to as low as 8,500 psi, 8.5 KSI for a thick, full depth, or excuse me, conventional flexible pavement with an 8-inch AC lift. Okay, what happens as you move horizontally from, quote, the loaded area? Stresses do what? Go up or go down in the granular material and the subgrade? Go down. Okay. If you look at the value of theta we get, that's basically under the load plate, okay? Then we're at 9-inch offset, 12 inches, etc. Look at these values you get for theta when you get out there at those points remote from the loaded area. You've got modulus values that are insignificant almost, right? In fact, they may be lower than the subgrade. There are several models around. This is the K theta to the N model that I prefer. This is the Uzon model, another popular model, which takes into account theta as well as the deviator stress. And this is some data from one of Errol's study for the North Carolina DOT, where he had the data and we pull this together. Notice these R-squared values for this model versus that model. Basically, they both capture the effect you're looking for. Okay, higher stress state, higher modulus, which is what we're all after. And when you start looking at this deviator stress calculation, sometimes that gets to be a bit of a challenge. You run an elastic layered program, start looking at what's going on at the bottom of a granular base. What do you see? Tensile stresses. You ever picked up, been by a stockpile of crushed stone? You ever picked a rock up? How many rocks come with it? None. What's the tensile strength of granular material? Very low or nothing. So, it's simply suggesting that that's not an easy calculation with an elastic layered program. Okay, HMA modulus, we need to take into account time of loading, temperature, frequency effects. We have to consider it. There's a lot of information out there on estimating that. The Federal Highway has a good summary of some of that information. It's all over the literature. And, I personally like the Hirsch model. It's simple, straightforward, based on basically VMA and the, quote, the modulus of the binder of the asphalt cement. It's a simple-minded approach, and it works very well. Ray Bonnequist, in fact, in the original paper said, hey, we can estimate the modulus probably closer than a lot of people can measure the modulus. So you say, oh, okay, then let's just estimate it. Okay, I'm not saying that's the only way, but it is a way. This particular summary report from FHWA, I think, is a good overall summary of the capabilities. Richard Kim's a very bright guy at North Carolina State. Structural models. Okay, we know modulus values, we know some thicknesses, we need to calculate what? Structural response. Well, you can always use the elastic layered program. The early work was what? Burmeister's procedure. Two-layered elastic system. We moved ahead from there. Currently in the MEPDG, the Jacob Uzan, okay, from Israel, linear elastic analysis, that's what that Julia stands for. Julia is also one of the major computational programs they use at Waterways Experiment Station. But when you move into trying to really represent the behavior of granular materials and subgrade soils, we need to account for what? Stress softening and stress hardening. Hey, that's the whole ballgame. Those things are not linear elastic. So we need to account for that. And you'll find that ILIPAVE is an axisymmetric finite element program, developed that back in the 60s. Lutfi Rod was one of the key guys helping us out from Berkeley. But it continues stress-dependent moduli. We have failure criteria. You just can't keep pounding stress on the granular materials and subgrades, right? They have a finite strength. You can't just keep on going. You have to stop and say, whoa, I've failed. I'm at the end of the line. That doesn't happen with linear elastic analysis. You just keep on climbing. And then, of course, you wind up with some challenges because the program is computationally insensitive. To do, quote, 3D analysis is very expensive. It's not being done. We use the concept of superposition. It seems to work out very well. And then we get into the 3D finite element scheme, and that's great. Then neural networks. Errol and some of his grad students and have done a lot of work. Neural networks are catching on. Hey, it captures the effects in a more straightforward way. We need to also look at some other issues. Anisotropy, that's a ET spatial over here, Toodlemer spatial, he likes that isotropy. And also residual stresses. They're important factors, but residual stresses in particular are really hard to take into account. I think the anisotropy stuff, they have some schemes that handle that very well. What's your GT PAVE? Yeah, it has an anisotropic capability. Transfer functions, stresses, strains, displacements, how do they relate to performance? Well, performance is a function of what? Distress, rutting, cracking in particular. And so we need to have these so-called transfer functions. This is a real important issue. It's one we continue to wrestle with even today. And I'll go through a few of these. Subgrade rutting. There are transfer functions. The early ones are based on subgrade vertical strain. More recently, based on work we've done in Illinois, we found subgrade stress ratio, i.e. subgrade deviator stress divided by unconfined strength, is a much better way of looking at the overall performance of a subgrade. Look at this. This work has a date of what? 1976. Frank Townsend was the lead on this. I've known Frank for years. I think he's retired. He's wiser than I am. He's retired and isn't working much. But anyway, if you try and relate resilient strain to the permanent strain that you develop under repeated loading, you get a plot like this. This is based on the Vicksburg buckshot clay. That's probably the most famous chunk of subgrade soil you'll ever find in the world. Look back in the Corps of Engineer literature, Vicksburg buckshot clay. It's all here every time. And it's still being used. They've got a good source. In fact, we haul Vicksburg buckshot clay from Jackson, Mississippi to the AAR test track at Colorado, what's the town? Pueblo, in order to build a soft subgrade section. All they had was sand. And Ernie Seelig and I said, hey, we need to have a soft grade. So we got the railroads who were sponsoring the project to haul a lot of Vicksburg buckshot clay down to Pueblo. But as you can see, for particular resilient strain, depending on the strength of the subgrade, you got different values of permanent strain or permanent deformation that develop. So it says, hey, this doesn't work, but yet it's being utilized widely. Sort of a summary of vertical strain versus design life. What's we've got here? We got the Asphalt Institute shell. That's to a rut depth of 0.5 inches. This is a PSI of 2.5, etc. And you can see these M values, the exponent here, stay about the same. The L values bounce around some. Mike Nunn at the UK TRL Transport Research Lab, in fact, in 2004, proposed, let's just go away. Let's not even do that anymore, trying to predict the problem and the permanent deformation in subgrade. And so they basically said, we got to build a working platform, a foundation. And so they have various classes of subgrades shown here. These are the modulus values for class 1, class 3, class 4, etc. And so in this particular procedure, they say, hey, you have to have this kind of a subgrade in order to move ahead in your design process. This is the original FAA relationship developed by the folks at Waterways Experiment Station in 1975, where they were looking at strain reps, modulus of the subgrade, and what we would have for a calculated strain. So this gives you the predicted fatigue life for a range of subgrades. But once again, it gets back to the idea of resilient strain, which is in many cases probably not working very well for us. This is the changed current FAA subgrade criteria for airport pavements. They bailed out on the original work that I just showed you, and they now are using this. If you have less than 12,000 coverages, you use that particular approach based on, notice here, this is an exponent of 8.1. Down here, it's 14.21. For this is what? Long life stuff out here, more than 12,000 coverages, basically. Okay, subgrade stress ratio, where we're looking at subgrade deviator stress divided by strength. This is work that Manny Bernardo and I did back in the early 2000s for the FAA Tech Center accelerated loading scheme. We were looking at a bunch of soils, and we found that subgrade stress ratio was obviously related to the development of permanent strain in a subgrade. And as you can see, this is lab data. We got the DuPont clay here in this case. If you're low stress states, you don't get much strain. If you go to 0.5, you get some, 7.5 more. And obviously, if you're loaded to 100% of its strength, you're going to get a considerable amount of permanent deformation. That one obviously is unstable. This is another one, different soil. And the same sort of thing shows up if you have increased stress states, regardless of the moisture content, you still have increased permanent deformation. So subgrade stress ratio is valid. We find it works very well. These are some early ideas. Franco Gomez and I proposed these for a meeting in Portugal with ISAP many years ago. And you can see for, quote, values 0.5, 0.6, you're going to last a long time. You move up to 0.75 or so, you'll have a more limited life. For those of you who have worked with CBR-based design for airfield pavements, you'll find that CBR is, quote, a magic procedure for evaluating subgrade soils in the Department of Defense for many, many years. Well, it still is, although not to the extent it was. Okay, well, if you divide unconfined compressor strength by 4.5, you'll get a value of CBR. So we have a connection we can develop between CBR and QU. If you look at the work that Walt Barker did at Waterways Experiment Station in conjunction with Carlos Gonzalez, they developed a value called beta, okay? beta is 3.14. What's that look like? Pi? Something like pi? Times the subgrade vertical stress divided by the CBR. That's beta. Okay, that's a beta term. All right. And they found, based on their analysis of a huge amount of performance data they had accumulated from their test tracks and other location, that log beta was related to C. C is what? Coverages. Now, coverage is a magic approach that the core uses to translate mixed traffic back into, quote, a value called coverage. So it takes into account the wander. And so if you look at it, you find that if you convert CBR back into QU, you get the subgrade stress ratio is the beta value divided by 14.1, okay? Look at this. This is a plot of beta versus subgrade stress ratio. Sure enough, if you want it to last a long time, you want a what? A low subgrade stress ratio. So beta is now into the Corps of Engineers procedure. They have bailed out basically on subgrade strain. So subgrade stress ratio is making an impact. If you got high volume pavements, you'll find in general the pavement sections are such subgrade rutting really isn't a problem, but you need a good subgrade support to build high type pavements. Granular material rutting, one way of covering that issue is make sure you get enough hot mix over the granular material so the stress states are low, so you don't get a lot of particular problem associated with that. And the MEPDG rutting model is there to be used, and we'll talk about that. Here's some work. Here's Errol's synthesis. This is actually a chunk of work. I suggest you look at that. You get a feedback on this? You get paid back any extra for references I might make, Errol? Okay. Appendix E of that particular synthesis, we have a couple of forms for permanent strain predictions, A plus B log N or A n to the B, and then the ULIS model, which includes what? A deviator stress term as well as a number of load reps term. This is the MEPDG rutting model. This is an excerpt from some of the work that Errol and some of his folks have done. And notice here that in all of this, you'll find that the magic term is the amount of permanent strain that develops related to the resilient strain you calculate. There is no, quote, stress term, right? No stress term. This is, once again, a little summary of some of Errol's work. Here is the particular rutting model again. Notice here we're emphasizing the effect, no stress state. I don't think you can predict permanent deformation without taking into account stress. This is a summary of some of the work, early work he did for North Carolina DOT, a range of values. They did shear strength testing, characterized materials, as well as modulus testing. Now here's the factor that you really need to keep in mind, shear stress ratio. Stress ratio is a most important parameter when you start predicting permanent deformation of granular materials. And we can measure shear strength. We've done it for years. We still do it. It works quite well. So that shear stress ratio is important. There's some of the work that information from Errol's study. And then you go to repeated load triax. That's his. was carried out in Reno, Nevada many years ago. They did a lot of sophisticated work with repeated shear strain testing, and is also, that model takes into account stress. Okay, these are the R squared they found for the databases. The standard errors, as you can see, they're all about 1/10 of an inch, the S sub E over S sub Y term, but they're all turned out to be about the same. And basically they say, look, if you reasonably calibrate these models, they'll work. Okay, calibration is not an easy thing or a cheap thing to do. So what's a reasonable prediction for a rut depth? If you're looking at a design of an interstate, what, failure is about 4/10 of an inch, primary route, 1/2 an inch, others, local roads and streets, maybe 6,500. These are values picked out of the MEPDG design criteria. How do you do HMA rutting? Material selection, do good aggregates work, do good mixed design work, pick the right asphalt, and do good construction quality control and assurance. You'll get a rut resistant mix. Rather than trying to predict values within 1/10 of an inch or so, you know, how much is 1/10 of an inch, folks? Huh? Heck, you can hardly measure it, right? So if you put down your effort in the mixed design, material selection, and construction, you get rut resistant pavements, and that's what we're after. But I'm not saying don't pursue trying to predict rutting, but keep in mind we can still build rut resistant hot mix asphalt mixture. HMA fatigue, this is the calibration from the MEPDG. Once again, notice S sub E over S sub Y for predicting alligator cracking. That's not a very good model. AASHTO type testing, beam testing, here we go. We've got these devices in the lab, a lot of work. Tensile strain, if you look at modulus, stiffness of the beam as a functional load reps, we lose modulus as a functional load reps. Ultimately, you get down to where you get failure. Failure is typically defined as what? 50% of the original value, something like that. If you do a lab algorithm of strain or life is K 1 over strain to the end, or K1 and K2, that's the intercept, that's the slope. You plot the data like this, extrapolate it, whatever. You get an improved K2. It does what? It flattens the curve out. And so keep in mind that if you go to a large K2, this thing almost becomes flat. You'll see a lot of K2s flopping around out there around 0.5. In this particular fatigue algorithm, that's one that is we've used and is in the Illinois DOT design guide. The MEPDG has a K2 and a K3 they bring into the stiffness, into the equation, the stiffness of the hot mix. It has an effect. The major driving factor, though, is the strain term. That value there is basically the one that dominates the fatigue of hot mix asphalt. Some work Sam Carpenter did years ago on fatigue and mixes in Illinois. In K1 over strain to the K2, the minimum K2 was 3.5. 90 percentile value was 4, which is a pretty good value. The average was 4.5. This shows a relation between K1 and K2. Once again, you do lab work and you get something plotting down here, you probably got a problem. We've worked with this for mixes. Every time I see any data with this kind of information, I crank it out and see how it compares. And every time it plots very close to that particular relationship. There is no unique fatigue algorithm for hot mix. We can assign one and use it for design, but that doesn't really mean we'll have that particular mix in the field. Remaining life, how long do we have left in an old pavement section that we're rehabbing? That is a major issue, continues to be worked out. Fatigue endurance limit. It's that particular value of strain below which we don't get any damage. If that's the case in a section with a perpetual pavement where we have a designed a fatigue endurance limit is controlling, we just periodically mill and fill the surface and we're home free. Carl Monosmith and a guy from Canada named McLean back in '72 came up with this particular article. paper, they found they were suggesting 70 microstrains of magic value. Okay, this is some work Sam did. Notice here, we're out here, yeah, what's that? That's 35 million. He's out there close to 40 million reps. And this particular mix went all the way. It's at 70 microstrain. That's a lot of popping it. 40-some million. Okay. The fatigue endurance limit is out there. It's not the same for all mixes. Sam did a lot of work trying to characterize this. He worked with 21 different mixes. The FEL, fatigue endurance limit, ranged from 90 to 300 microstrain. The average is 125. Mike Nunn in 1997, the UK guy, TRL. Mike first popped up this idea of these long life pavements. And then we have the group, the Asphalt Pavement Alliance. It's basically NAPA and the Asphalt Institute getting together, and they were proposing this bit of perpetual pavements that last forever in fatigue, just restore the surface. And Mike Nunn and his colleagues at TRL put together this particular report, which is excellent. I suggest you get it if you don't have it. It goes into their experiences in developing the concept of long life pavements. Sam Carpenter and I did a dog and pony show at Auburn. This is ISAP Symposium on Design and Construction of Long Lasting Pavement. And we pulled together Sam's work and some of the work we've been doing on the LE pave analysis. This is basically what you're suggesting. All right, if we get a strain value of 70 microstrain or less, it's perpetual, no fatigue failure. The problem is, what's the fatigue endurance limit, right? What's K1 and K2? Current INSHRP research on the problem, that project has been finished at the NCAT at Auburn University. Sam Carpenter participated in that, by the way. And then there was a plan developed for pursuing the fatigue endurance limit issue, and that resulted in INSHRP 944A. Matt Witzak moved to Arizona State, and so Matt Witzak and Mike Mamluke ran that project. Here's what they found. Fatigue endurance limit is not constant for a given HMA, okay? No such thing as a given value. It varies with a modulus. You get a smaller fatigue endurance limit for high modulus materials. Throw in a rest period. In other words, instead of going bump, 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 provide a little rest between load reps, and you'll find that the fatigue life increases. This shows that effect. I ran this particular procedure they proposed for a section here in Illinois, a 10-inch full depth pavement, various moduli values. If you have a 1 second rest period, that's the fatigue endurance limit in microstrain. You got a 5 second rest period, this is what you get. Considerable difference. Factor what? 3, something of that sort. So that's of some significance. There is a current project underway, but with Ray Bonnequist and Don Christensen at Advanced Asphalt Technology for completion in 2017. Binder, fatigue, fracture, and healing, and their contribution to hot mix asphalt fatigue performance. We're anxiously awaiting their inputs. Our perspective on perpetual pavements, that's hard to say quickly, in Illinois is this. We look at the hottest month of the year, which is July. We predict the modulus for that month and say, okay, what's the strain value for that particular temperature? And we compare it to our criteria. In Illinois, we picked up with 70 microstrain. That's a very conservative value, by the way. But that's the way we do it. Design reliability. Are we working with average values? We try to work with 90 percentile values, etc. What can you measure about a pavement? Structural response in terms of deflection. We're interested in stresses, strains, and deflection. Of those, that value there, the deflection, is the one we can easily measure. And we can do it with a falling weight deflectometer, a rolling wheel deflectometer, or a travel speed deflectometer. We look at the variability in those deflections, and we can relate that to performance. The SCI, Surface Curvature Index, is the deflection at the center of the load plate minus the deflection of 12-inch offset, or this is a preferred value. It's one Howard Hill and I developed many, many years ago called AUPP. That's AUPP. Basically, it takes out the effect of the subgrade. It basically looks at the overall behavior of the hot mix section. We can relate deflection to strain for our full depth sections in Illinois based on that equation. We validated that. The subgrade stress ratio we can predict as a function of delta naught. Log of strain here is a function of AUPP. We didn't use this for many years. We confirmed it hardcore. Minnesota road test has been used it ever since. It's a valid relationship and works very well. Conventional flexible pavement, same thing. Strain in the asphalt, stress ratios, strain as a function of AUPP. Once again, you can measure these displacements under FWD loading, TSD, or RWD loading. Okay, observations and a summary. We've come a long way in the last 60 years, and we're getting better all the time. Notice we're not consistently satisfactory. That's a nice way of saying we suck at doing some of this stuff, okay? Got to be politically correct here, right? Nevertheless, calibration does improve things, and we continue to try and calibrate. However, we need to go to finite element models. We need to accommodate stress dependency. We need a failure criteria. The idea of anisotropy, residual stresses. We need to reconcile lab and field. Whenever you do a lab test and get a number, you do a field test to back calculate a modulus and you're off a factor 2, you say, wow, we must have a problem here. Okay, we need to continue to refine our characterization procedures for modulus, strength, failure criteria, and fatigue, improve transfer function. Let me pick a transfer function. I can get you any pavement section you'd like to build. Okay, no problem. It may not work, but you know, if your transfer function is appropriate, okay. We need cumulative damage models that are better, stress history effects. We need to have reasonable expectations, folks. Hey, you know, we're working with materials that are in the ground somewhere in the world. The asphalt comes from somewhere, you know, it shows up in our project and we take it and use it. So trying to predict some of these things within 15 load reps or 5/100ths of an inch permanent deformation may be somewhat under-realistic. However, we are progressing. Keep up the good work. I've done my part. It's all up to you folks down here. So pick up the flag and charge ahead, okay? Now here are some principles. Don't forget these, folks. Write these down up there. Put them in an important spot. Do not measure with a micrometer, mark with a grease pencil, and cut with an axe. What's that say? Keep things in perspective, okay? You got a super sophisticated model and we're feeding garbage into this thing, you don't get a very good answer, okay? So keep those in mind, and I frequently use this saying. I'm noted for that. My students all frequently bang on me about this particular set of principles. Okay, thank you very much. Enjoyed it. And if you have any questions, we'd be glad to respond to those. Any questions? Don't feel that I'm not overpowered, you know. I don't bite or anything like that. So, a lot of material. But it's a challenging issue. Hey, it's a issue of most important. I'd suggest now that a lot of our emphasis needs to be moved toward, you know, sustainability, in-place recycling, this sort of thing. As you move into those kind of materials, folks, we're going to hit even bigger issues in some of these problems that we've been discussing here today. Okay. Virgin materials. Hey, I like it. Virgin materials, wide open construction, new stuff. Oh, that's great. We're not doing a lot of that. A lot of our money at IDOT and other DOTs nationally is going into what? Rehab, rehabilitation, et cetera, et cetera. And those problems are very difficult to handle. Okay? Good. Dr. Okadi back there, he just looked and studied.
Actually, Marshall, I really appreciate that you're here, and this has been quoted by a lot of people that this is Marshall statement, but I wanted to share with everybody that when I was a student, there's always 4 people that I wanted to meet in my life, and Tom Kennedy was one of them, and Carl Monosmith, and Marshall Thompson, and Sam Carpenter. So these people were, when I was a student, these people were my heroes that I really wanted to meet them and learn from them. And I remember one time as a student, I paid for a ticket just to go and travel at that time to hear Tom Kennedy. So that will tell you that it's so important to learn from the right people. And what Marshall has done to our profession is beyond what you can imagine. I mean, he really wrote, I mean, if you look at the Illipave was way above what was happening at that time, okay? But that was coupled with something which is important, which is the real life thing. So what he has in the last slide is, guys, it is so important that we are working with micromechanics, we're working with finite element, but at the end of the day, if you don't know what we are dealing with, you will never understand it. And I think that's maybe to you, Isaac, when you came in, you want to work with these things. I said you need to go to the lab, spend some time in the lab, so in the future, because he's the new kid in the block, that's why I pointed it out. So at least in the future, you will be able to relate what you are doing. So the other point that I was making here is you always need to do your best. I mean, I myself never thought when I was a student that I will be a colleague of Marshall Thompson. Okay? So Marshall, we appreciate you all the time.
Thank you. Thank you. Comment about, you know, sophistication, etc. I think we need to acknowledge that, you know, pavement technology, material science, and all of these are very, very important issues. I mean, we're all for them. Carl Monosmith points this out in his first Monosmith lecture, which goes back a few years. It's out on the website, by the way, if you want to look at it. But he emphasizes that ultimately you get down to the problem of what materials are we going to use and how thick they're going to be. Okay, the layers, etc. And there are a bunch of important inputs in terms of material science and advanced analysis schemes, etc. Ultimately, you got to get it down to something that can be utilized. And you'd be surprised how many pavement design engineers you think you'll only do with T's got on their staff. There are a couple of folks down there that dabble in pavement design. That's it.
Listening to you.
Huh?
They're listening to you.
Oh, yeah. Hey, I just would encourage it, you know, and they do a good job. You know, I'm talking about Chip Weinreich and LaDonna and Amy Schutzbach, okay? And they're there. They're doing their thing. But, you know, ultimately, you know, you get everything reduced down to what? Policies and procedures. Okay, we just need to make sure that our policies and procedures are as good as they possibly can be. So, all right, thank you.
Thanks, Marshall.
Most factors up into a corner there. Arranging partnerships to the